This is Math 1090, Section 2.1, Systems of Linear Equations, Part 2. Okay, let's get back to where we left off. And that was solving a system by elimination. Okay, I'm going to demonstrate this right away, but let's just go through the steps quickly. So first you want to write both equations with the x and y variables on the left side of the equal sign and the constant terms on the right. And we want to make sure to line up the variables. Step 2, if one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation, add the equations together, eliminating one of the variables. Now usually that won't happen, but so in that case, so if not, use multiplication by a non-zero constant so that one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation. So we're just going to multiply one of the equations by something so that we can get cancellation. And sometimes you actually have to multiply maybe both equations by something to get cancellation, and that's okay too. And then you add the equations to eliminate one of the variables. Step 3, solve the resulting equation from part 2 for the remaining variable. And finally, step 4, substitute the value from step 3 into either of the original equations and solve for the second variable. Okay, so that's going to be hard to follow, but an example will make this much clearer. So we're going to solve the following system. Now, we could eliminate either variable, it really doesn't matter here, but let's eliminate x from the system. To eliminate x from the system, notice that if I were to multiply the first equation by 2, then I'd end up with negative 2x plus 2y equals negative 10, right? And then if I add the equations together, the left sides of the equations, add those together, add the right sides of the equations together, then the x terms will cancel out. So what I mean is this, if I call this equation 1 and I call this second equation equation 2, then what I'm going to do in kind of a shorthand notation is I'm going to multiply equation 1 by 2, and then to that I'm just going to add plain old equation 2 and get the result. So 2 times equation 1 is negative 2x plus 2y equals negative 10. And then the second equation, just rewrite it down here, 2x minus 5y equals 1. Okay, like I said, we add these together and the x's will be eliminated, hence the name Method of Elimination. And what am I left with? I'm left with negative 3y equals negative 9. So, of course, y equals 3. And there we go. We've solved for one of the variables. Okay, now, we can now take that. So that is steps. So step 1 was already done for us, right? This is step 1 right here. Step 2 here is where I multiplied the first equation by a non-zero constant. In this case, I multiplied by 2. Okay, and then step 3 was right here where I solved the resulting equation. The resulting equation was negative 3y equals negative 9, and I solved that for the remaining variable, which in this case was y. And now we need to do step 4. Step 4 is substitute the value from step 3 into either of the original equations and solve for the second variable. So it doesn't matter whether we put this value of y equals 3 into equation 1 or 2 and then solve for x. Either way we'll get the same answer. So I'll just plug it into equation 1. So we get negative x plus 3 equals negative 5. And then of course I'm going to subtract 3 from both sides, and I get negative x equals negative 8. So x equals 8. Alright, and there we go. That's the method of elimination. It's pretty easy. And I just want to point out one thing here. Notice, what are we doing? We're taking the original system of equations was 2 by 2. Okay, that first number in 2 by 2 refers to the number of equations. The second refers to the number of variables. We have 2 variables, x and y. So we started with a 2 by 2 system. And then what did we get here? Right here, we were able to eliminate one of the variables, and we got a 1 by 1 system. Okay? So that's the key. We're taking this method is a divide and conquer type of algorithm, where we take a difficult problem and we reduce it down into a simpler, slightly simpler problem. Well, much simpler problem, right? If you have an equation in one variable, we know how to solve that kind of problem. So, and the thing I want to point out here as well is that this method of elimination is probably the most important method for solving systems of linear equations, because it is conducive to scaling up to larger systems. Okay. Now you can certainly use like the substitution method to solve a 3 by 3 or 4 by 4 system, and even larger systems, but I think it gets a kind of messy, a little bit difficult to do. It works, but what you'll see is the method of elimination is what we really use to solve larger systems of equations, like 5 by 5 and 10 by 10. And in real life, it's not uncommon to have something like a 1,000 by 1,000 system. In fact, Google pioneered how to solve billion by billion systems, or how to solve billion by billion systems and beyond even. So it's very important and has lots of uses, and the elimination method is really what we're going to use to ramp up, and we'll see that in the next section. Okay, moving on, let's do some more. Let's see some more examples here, and I'll use elimination on these exercises as well. So Todd has just retired and has $810,000 to invest to fund his retirement. He found a very safe certificate of deposit, or CD account, that pays 2% interest, and a riskier bond fund that pays 6% in interest. Todd figures he needs $28,000 a year to live on. How much should he invest in each account to make enough money that he could live off the interest alone while minimizing his risk? So Todd has a nest egg for his retirement of $810,000, and he wants to put this into an interest-bearing account, in fact 2 different accounts, such that the interest alone will be $28,000 a year. But he wants to put as much as he possibly can into the safe account, the safer bet, and that is the certificate of deposit, typically a very safe investment, but yet low yield on interest, right? And then he'll put the rest into the riskier, but still probably fairly safe 6% interest. Okay. How can we model this problem as a linear system? Well, we need to figure out what are the variables. That's the first thing. And the 2 things that can vary that I see are how much he invests into the CD and how much he invests into the bond fund. So let's make that explicit, and let's say we'll let X be the amount in the CD, and we'll let the variable y represent the amount in the bond fund. Okay, in dollars. So let's see. So we've introduced some variables, and now what we need to do is extract. Because we have two variables, we need a 2x2 system of linear equations in order to be able to uniquely solve for both variables. With just one equation, it won't be enough. We need two. So let's see, how can we extract two equations from this description? Well, first, I see that number $810,000 is what he has. So the total amount that he invests has to sum to $810,000. So that means x plus y has to equal $810,000. So let's write that equation down. We have x plus y equals 810,000. Okay, and next we have the interest. He wants to live off of $28,000 a year, and he from interest, right? So what is the interest he'll gain each year from the X dollars he puts into the CD? Well, it'll be, since it's 2% interest, it'll be 0.02x. Okay, that's the interest that he'll get each year from the amount he invests in the CD. So, and then the amount he'll get in interest from the bond fund will be 0.06 times y, because y is the amount invested in the bond fund. And in total, when we add those two interest amounts together, we get the total interest, which needs to sum to 28,000. So there's another equation. So we have 0.02x plus 0.06y equals 28,000. There we go. There's our system. Now, one thing that is a little unpleasant about this system is the decimal. It's perfectly fine. It's perfectly fine to leave those values as decimals, but I would just want to show you something that's perfectly legitimate to do that might make our lives a little easier. And this is a useful little trick, and that is I want to clear out those decimals, right? And so I'm just going to multiply the second equation by 100. Okay, because what is 0.02 and 0.06? It's just 2 100ths and 6 100ths. So I'm going to multiply that second equation by 100, clear out decimals entirely, and I'm going to get a new but equivalent system. So my equivalent system will be x plus y equals 810,000. First equation stays the same, but the second equation will now become 2x plus 6y equals, and then I got to tack on 2 more zeros. Multiplying by 100 will tack on 2 more zeros to that number, and that's going to give me, let's see, 2800000. Now I put the commas in the appropriate places. I get 2.8 million. Okay, so this is an equivalent system, but it has no decimal points in it. It's a little nicer. Do I need to do this? Nope. Nope. I could still do the method of elimination with the previous system, but I kind of prefer this. Okay, now in the previous example I eliminated the x variable first. Let's eliminate y here. So to do that, what am I going to do? I'm going to, in order to eliminate the y's from these two equations, notice if I multiply, let's call this equation 1, and this will be equation 2. If I multiply equation 1 by -6, and then add the equations, the y's will be eliminated. So let's do that. I'm going to do -6 times equation 1 added to equation 2. Okay. And what am I going to get? I'm going to get negative 6x minus 6y equals, and then negative 6 times 810,000. I'll do that on the calculator. Negative 6 times 810,000. That's negative 4.86 million. Okay. And the second equation just stays as is. I have 2x plus 6y equals 2.8 million. Okay, I add these together, and what do I get? I get negative 4x. I'll write it up here. I get negative 4x equals, let's see, negative 4,860,000 plus 2,800,000. Well, I can just add that to my previous result, so I'll do plus 2,800,000. Okay, and I get negative $2,060,000. Okay, I want to divide both sides by negative 4, so I hit divide by negative 4, and I get 550. So x equals $515,000. Okay, that's a reasonable value. He has $810,000 to begin with. He's going to put $515,000 into the CD account, and then to solve for y, well, I'll just use equation 1. So equation 1 says x plus y have to sum to 810,000, right? So I have this equation, 515,000 plus y equals 810,000. Solve for y by subtracting 515,000 from both sides, and I get, I'll do it on the calculator, why not? 810 minus 515, that's 295,000. All right, so Todd should invest $515,000 into the relatively safe CD and $295,000 into the riskier bond fund. Okay. Next example. A store owner wants to mix chocolate and nuts to make a new candy. How many pounds of chocolate, C, which costs $18.10 per pound, should be mixed with in pounds of nuts that cost $2.90 per pound to create 20 pounds of a mixture worth $8.29 per pound? Okay, I bet you didn't know that a chocolatier would need algebra to do their work, but apparently you sometimes do. Hey, huh? Math is everywhere. So let's see here. They gave us the variables to use: C for pounds of chocolate and N for pounds of nuts. So that's kind of nice. That makes sense. Now we need to extract two linear equations from this description of the problem. I think the simplest would be, we want to create 20 pounds of this mixture, 20 pounds in total. So, and since C, the units of C and N are both pounds, when we add C plus N, that has to be 20. Okay, so the first equation is C plus N equals 20. Now, the next equation, what should it be? Well, let's see here. Let's look at these numbers. So the chocolate cost $18.10 per pound. So if I multiply the C times 18.10, that's going to give me the cost for the chocolate. Okay? So, and then if I multiply in by 290, I'm going to get the cost for the nuts. Okay? And then I can add that together and get the total cost for the mixture, right? Okay, so let's see here. Let's do 18.10 times C plus 2.9 times N, and this should equal 829, right? Okay, now you might be tempted to, this is actually wrong. And the reason it's wrong is because this 829 is per pound. So I've got to multiply, in order to, because on the left-hand side of this equation I have units of just dollars, not dollars per pound, because I'm multiplying the cost by the number of pounds to just get dollars. So on the left side of the equation I have dollars, so I need dollars on the right side of the equation as well. So I need to multiply the $8.29 per pound times the number of pounds in the total mixture, which is 20. So 20 times 8.29. And there we go. There's our system of linear equations. Okay, first thing I'm going to do is multiply that right-hand side out. Let's see, so we get 20 times 8.29, 165.8. Okay, I'll just write that below. Okay, you know what I think I'm going to do here is clear out the decimals again. This time, usually when you have dollars and cents, you need to multiply by 100, but actually it'll suffice to just multiply the second equation by 10 here. So let's do that. So my new system will be C plus N equals 20, and then I'm going to have 181C plus 29N equals 1,658. Okay, there we go. So this is going to be the system I'm going to solve by the method of elimination. And I'm going to show you a slightly different way of doing it than I did it in the previous two examples. Okay, what I'm going to do is I'm going to use the method of elimination, kind of like, well, just a variation on it. So let's see here. What should we do? Let's eliminate the C variable. Okay, so I'm going to do that by multiplying the first equation by negative 181. Why? Because when I do this, watch what happens. I get negative 181C minus 181N equals, let's see, what's 181 times 20? I get, so negative 3620. Okay, and then the second equation is just 181C plus 29N equals 1658. Okay, so the point is that I multiplied the first equation by negative 181 because now you see when I add the left-hand side of the equations, the left-hand sides, and the c's will be eliminated. Okay, so we literally want to add the left-hand sides and the right-hand sides. On the left, what do we get? We get, let's see, what is negative 181 plus 29? Negative 152. So we get negative 152n is equal to negative 3620 plus 1658. This is equal to negative 1962. All right. And divide both sides by negative 152. So divide that last answer by negative 152. And I get we're measuring in pounds, so I think the nearest hundredth of a pound will be sufficient. So I'll say this is N is approximately 12.91. Okay. There we go. We've solved for how many pounds of nuts we need. How much chocolate do we need? Well, the regular method of elimination, I would just take this value now and then substitute it back into either one of the original equations and solve for C. And clearly, because C plus N equals 20, I need, what would it be? It would be 7.09, I think, right? Yeah, because 12.91 plus 7.09 is going to sum to 20 pounds. So C is 7.09, okay? And that's the normal method of elimination when you only have two equations. But it doesn't work so well. Well, it works. It still works when you have more than just two equations. But I want to demonstrate another technique you can do, and that is simply I can do this method twice. The thing I just did. I could have solved, instead of solving the system for N, I could have solved it for C by eliminating N. So let's do that. To eliminate N, what do I need to do? I'm sorry, to eliminate C. Oh, no, yeah, I was right. To eliminate N, what do I need to do? I need to multiply the first equation by negative 29. And so I'm going to get this system. I'm going to get negative 29C minus 29N equals, and then, let's see, negative 29 times 20 is negative 580. And then I'm going to add that to the original second equation, which is 181C plus 29N equals 1658. Okay, and now you see that the N's will cancel, and I'll be left with just some C's. Let's see, 181 minus 29 is 152. So I'm left with 152C equals, and then we want to do 1658 minus 580 is 1078. Okay, divide both sides of this equation by 152, and I get I get 7.09. There we go. So the solution is to make a mixture of 7.09 pounds of chocolate with 12.91 pounds of nuts. There you go. Just for completeness sake, I'll accept this kind of way of giving me your answer if you need to give me a written answer, but what would be a preferable way to report the answer? Well, remember, when solving a system, we're finding the set of all points that satisfy all the equations simultaneously. So a preferable way of reporting the solution would be to say the set containing the point let's see, I guess we could put chocolate first, since alphabetically it comes before, C comes before N. So we would say 7.09, comma, 12.91. Okay, and it's a small detail, but that would be a preferable way to report the solution. All right, and this concludes section 2.1.